Welcome. Today we're going to talk about fields in it's a higher level topic on the IB diploma program, and we're going to focus on gravitational fields today. Let's take a new slide. Well, we know from a previous chapter that around a mass m, or if I put a small test mass little m next to a big mass of big M, then there is a gravitational field or rather we've been talking about that there is a force which is equal to the gravitational constant times by product of the masses and divided by the square of the distance between them. And we've also been talking about gravitational field strength, little g, which is the force per unit mass, which is equal to, therefore, big G times the mass of the big mass divided by the square of the radius. Now, I can also imagine myself putting this test mass over here, or over here, or over here, and wherever I put it, it's going to be pulled into this big mass M here. So we can invent something called a gravitational field around this big mass M, which shows the direction in which a test mass would travel if put in the vicinity of big mass M. And these are straight lines which are all perpendicular to the surface of this sphere, radiating inwards, and the arrows show the direction. And the analogy here, or field lines, we're also going to talk about field lines for charged particles, and for a small spherical point charge, then the field lines look much the same, but we'll talk about that in another video. Let's create another slide here. What happens though if we come close to the center of the Earth, which is a large spherical massive body? If we stand on the Earth here, then the Earth looks roughly flat. Well, in this case, the field lines look like this. If I put a small test mass in, if I raise it from the surface of the Earth, it's going to want to get pulled down back straight to the Earth. So the field lines are not radial, but they are parallel and roughly equally spaced because the field is uniform. And they're still perpendicular to the surface. Let's take a new slide. Let's talk about another concept. And that is the concept of gravitational potential energy. And we have used an approximation of this previously. If we have the surface of the Earth and we have a mass and we raise it a height delta H, then we've given it gravitational potential energy mg delta H. Well, it gets slightly different if we have spherical bodies. If we have a mass m here and we have a small test mass little m here, then there is a gravitational potential between these two bodies, and it's defined as gravitational potential energy is defined as the work done in bringing the bodies to their present position from being infinitely apart. So I can imagine having, when m was at infinity, and then bring it into its current position, which is a distance r from the center of big M. The work done in doing that is equivalent to the gravitational potential energy. And this can be written using calculus. So the work done is the integral from infinity to r of the force. This is the gravitational force over dr. And this integrates to negative, because you have a 1 upon r squared here, or r to the minus 2, negative big G m little m over just r now, and the limits remain from infinity to r. So this becomes negative G m m over r. So the gravitational potential energy, which is shortened to E subscript P, is equal to minus big G m little m over r squared. So in fact, the negative here means that we have gained energy, if you like, bring it from here to here, and we would have to then use energy to take it back out to infinity. Another way of thinking of this is, if I have a new slide, if we have the surface of the Earth, and we imagine a mass little m on the Earth has mass big M, then we can imagine little m sitting in what's called a potential well, and when it's at the bottom of this potential well, it has gravitational potential energy minus big G m, big M, little m over R, where R is the separation between the centres of the masses. And then to lift this out of the potential well, it's going to take energy and only theoretically it's going to have zero potential energy at infinity. So we have to then do work on the mass to get it from the bottom of the well out of this potential well. Let's just do an example calculation. We are told to calculate the difference in potential energy of a satellite of mass 1500 kilograms. So here we have taken away from the surface of the Earth to a distance 520 kilometers above the Earth's surface. This is out of proportion, this diagram, just so you know that. So here we have the Earth, here we have the satellite whose mass is 1500 kilograms, and we're going to raise it from the surface of the Earth a distance 520 kilometers. We're told that the Earth has mass 5.97 times 10 to the 24 kilograms. And what else do we need to know? We need to know the radius of the Earth. 6.38 times 10 to the 6 meters. So we want to work out the change in potential energy. So basically I want to work out the potential here and then the potential here and then find the difference. So let's call this point A and this point B. So at A, the gravitational potential energy at A is minus G times big M, little m over RE. If I plug in the numbers, I get, let's see, negative 6.67 times 10 to the minus 11 times the mass of the Earth, 5.97 times 10 to the 24 times 1500 divided by only the radius of the Earth, which is 6.38 times 10 to the 6. Let's get out my calculator, which might look a bit like this. Negative 6.67 times 10 to the negative 11 times 5.97 times times 10 to the 24 times 1500 divided by 6.38 times 10 to the 6 gives me minus 9.4 times 10 to the 10. And what are the units? Well, it's an energy, so the units are joules. And if you plug in the numbers, do the same thing at B, but this time the radius is the radius of the Earth plus 520 kilometers. You get minus 8.7 times 10 to the 10 joules, and therefore the difference between these two is minus 8.7 minus 9.4 times 10 to the 10, which gives you 7 times 10 to the 9 joules.